This Fizzcast will be looking at the photon nature of light. You might like to pause the video and read carefully through the question. Now that you've read through the question, you can see what's being examined here is how many photons are arriving per unit time for this beam, this laser beam here, of a power of 1 milliwatt, a diameter of 2 millimeters, and you're told it's a green laser beam. Now we need to think a little bit about this nature of light. There's two pictures we can use to think about how light operates. One that you might be familiar with is this idea that as light's moving along, perhaps moving along in space here, that it actually acts like some time-varying electric field here. You might put electric field on that axis, and at the same time there's also, at right angles to that, a time-varying magnetic field. And both of those are at right angles to the direction in which the light is moving. And that's this idea here of an electromagnetic wave that we're quite familiar with. And something else that might be understood there is that the energy in this particular wave is proportional to the amplitude of those fields squared. The other picture we now have is that light can be thought of as a bunch of small little pieces, each of them moving along at the speed of light. But rather than a continuous thing, it's a little piece by piece thing. It's a particle picture. So here we're thinking about light as a stream of particles, which of course we refer to as photons. And here the important thing is that the energy we have is now proportional to the number of photons. And it's also proportional to how much energy each photon has. Where it's important that we understand that the photon energy here, as given by Planck, is Planck's constant multiplied by the frequency, or if we like to deal with it in terms of wavelength, Planck's constant times the speed of light divided by wavelength. So in this problem we're told we have the total power of our beam of light is 1 milliwatt, so that's 10 to the minus 3 of a watt. We're told it's a green laser beam. We need to know something about the frequency or wavelength here, so telling us green isn't perhaps an exact value, but we could look up and see that we can say, let's approximate our green laser as having something like 550 nanometers. So we might not get an exact number out of this, but we might still be able to answer this second question here about whether we expect to reveal the photon nature of light by looking at how many photons are arriving here. The other thing we're told here is that this beam has a diameter of 2 millimeters. Remember, power here, of course, is energy per unit time. And we should be able to think about the energy here in terms of photons, and the time here is because it's asking us about how many photons arrive per unit time every second. And we can see in all of our relationships we've got here, there's actually no need to use this particular bit of information here. Our diameter of 2 millimeters doesn't give us any important information for calculating what this question's asking here. And that's an important point when you're looking at questions like this. You want to be thinking about what kind of question is it, what is it asking, what are the important quantities that I need to understand, because maybe the question has given you some things that you don't need. You don't always need to include every quantity that's been given to you in your calculation. And in fact, in this case, you weren't really told one of the important quantities. You were told it was a green laser beam, but we've now made sort of some kind of approximation here. Without knowing anything further, we'll just approximate that wavelength was going to be something like 550 nanometers. That's something you might have to look up, or something you might have a bit of a feel for. But importantly now, with the energy of each photon and with our power that we're given and the wavelength that we've kind of assumed here, we've got enough information to calculate how many photons are arriving. So the number of photons will simply be how much energy per unit time is arriving, that's this power here, divided by the energy of each photon. And remember, power here is energy per time. The energy of the photon is just energy. So this will give us a quantity per second. And that's what we want to get in the end. So now we can write this out, at least symbolically for now, as power divided by the photon energy, or multiplied by the reciprocal, so lambda over hc. And these are all things that we have values for. So our power here was a milliwatt, 10 to the minus 3 of a watt. Our wavelength here we're going to assume is something like 550 nanometers, so that's times 10 to the minus 9. We'll divide that by Planck's constant, 6.63 by 10 to the minus 34 in units of joule seconds, multiplied by the speed of light, 3 times 10 to the power of 8 in meters per second. When we do that calculation, we should get a number here, and if you do that calculation, I say the number you get there is something like 2.8 times 10 to the power of 15, and that's basically photons per second, because we've got a power divided by an energy. So there's our answer, and it's a very large number, as you might have anticipated. Maybe it's not exactly the number you would have guessed, but maybe you would have thought it was going to be a large number anyway. So you haven't got like 1 million photons arriving per second, or 1 billion, or even 1 trillion. This is a very, very large number. It's kind of easy to lose track of how large these numbers are when you're using scientific notation. 10 to the power of 15 is indeed a very large number. So that's how many photons are arriving per second. There'll be, of course, some kind of efficiency in the conversion of those photons to an electrical signal in our photodiode, but we certainly would not expect that many things arriving per second to be distinguishable in our signal. In a sense, you can think about this like if you're looking at a stream of water, say flowing from a tap. It looks like a continuous flow of material, but you know that at some level it's really coming out as a bunch of H2O molecules. But because there's so many of them coming out, you can't really distinguish molecule by molecule as it's coming, say compared to perhaps sand flowing through an hourglass. If you look up close to that, you can see it, whilst it might look a little bit like a continuous flow, you can actually see it's composed of a whole bunch of distinct grains as they're coming through. But that's because there's probably only maybe tens to hundreds of grains moving past every second, and you can actually distinguish those. If it's 10 to the power of 15 particles per second, it's not going to be possible in some sort of straightforward measurement at least to distinguish that from a continuous flow, something more like a wave. So although our photon picture does match our experimental measurements in things like the photoelectric effect, it's really important to know it there. We also know there's a wave picture of light. Both of those have to be true, and they've kind of got to be true at the same time. That's something we'll be dealing with in quantum mechanics. But in this particular instance, we can see that for something like a 1 milliwatt beam of light, that particle nature is going to be swamped by the sheer number of photons per second that are actually in that light beam.